All right, welcome to Chapter 7, Section 5, called Similar Triangles and Indirect Measurement. So this is for Math 8. The first thing that you'll see on your screen here is a due date. I don't see it on my teacher preview, but you'll see it on your student screen. The second thing is the number of attempts. We always allow unlimited attempts on homework, tests, and quizzes, so you can come in and try this assignment as many times as you would like. Number of questions just tells you how many questions are on this assignment. Best grading policy is always best score, so whichever attempt is the best is the one you get to keep. Partial credit's enabled, meaning if you answer one of 4 questions correctly, you get credit for 1 question, or however many you answered correctly. Down here it says, please remember once you start your homework, you must finish it before you can work on anything else. That means once I click start, down here in the bottom right corner will be a submit assignment button. I need to make sure that I click that submit assignment button when I want to leave this screen. So whether or not I've started any of them, or some, or maybe all of them, I always want to click submit assignment. I don't want to just close the tab or close my computer, because Alex is going to assume that I want to leave this attempt open if I don't click submit assignment. Remember, you have unlimited attempts on the assignment. You don't need to leave the attempt open. As long as you have a green check mark, it's going to save your place, meaning you don't have to repeat those again. It's going to start up right where you left off, and it won't lock you out of everything, like we just said on that first screen. The second big reason you want to click that submit assignment button is so your teacher can actually see what you've been working on. It affects the grade book that way. Otherwise, your account's kind of just on pause. We don't get to see what you've been working on. So, good idea. Just always click on it. On the side here, you can see sometimes there's a calculator. It's not always there, but right now we do have a calculator. Explanation, example, and message center. So explanation tells us we're going to lose our current question attempt because it's going to give us the solution or answer to this question. It's not going to give you the answer and then let you come type it in. Example will give you an example of something very similar to what we're looking at. So it gives us a diagram with 2 right triangles in it, just like we're looking at on the other screen. And it shows us the procedure, or kind of their method for walking through how to do this. Once you're happy with that explanation, you can close this, or not explanation, that example. You can close it, you can open another example. It'll give you a brand new one. Or you can also message your teacher directly from the screen, so that when you reach out, it attaches a picture of what you're working on so we know where to come help you. All right, let's go ahead and get started with this one. So in the example, what it was showing there was, why don't I see my color wheel? Interesting. All right, usually a little color wheel pops up here, but it's hidden from me. So in the example, what they show, and I'm just going to draw this over here, and when you draw this diagram, it doesn't need to be perfect, something like that, and I can see that there's these 2 little squares. What that means is these are right angles. Right. And this guy is a right angle. So I have 2 right angles here. And we're under the assumption that these are similar. We can actually go through and prove this using angle-angle similarity. We didn't really go through this property as far as actually teaching it in the class. They just kind of started throwing it at us. So angle-angle similarity means if I have 2 angles of one triangle that are congruent to 2 angles of another triangle, the triangles are similar. Not necessarily congruent, but they're similar. They could be congruent, but we'll just call them similar because we don't necessarily know. And in this case, we can kind of see this guy is much smaller than this one, so they're not congruent. Congruent means same size and shape. So similar means they're the same shape, not necessarily the same size. So the reason we can use angle-angle is because if I go, anytime I have like an X with 2 lines, which I can see in the middle here, I can go across the vertex, and this is called vertical angle. So this is a vertical angle, and anytime I can do that, a vertical angle is congruent. So I have angle, angle on the bottom triangle here, and angle, angle on the top triangle. So they are similar triangles. All right, I'm going to take some of this stuff away here just so it gets out of our way, because I think that's too much junk in the way. So let's go ahead and put the measurements they have here. So they give us 5 for this one, 3, 7.5, and x. And they want us to find x. So what they do, if you look at the example, I guess I'll put it in pink, they go around and they label the triangle. So they go like A, B, C, D, E, something like that. So they give all the vertices a name. So then they can go A, B, corresponds to DE. And DC corresponds to BC. So this just gives us a way of naming it. The other way that I tend to do it is I look at kind of the direction of what I'm doing. So if I'm looking at this one, I have this far point or far vertice, and it's going to the right angle, like that. So I can describe the other one the same way. So I go to the other triangle, I have this far vertice, so this one that's kind of out away from everything. And if I go to the right angle, these two are corresponding sides. I kind of like to describe it that way. It makes a little bit more sense generally when I'm starting to teach this to students, when you can kind of use these descriptions. So you have this far off vertice going to the right angle, far off vertice going to the right angle. It just kind of gives this direction, this visual direction. So these guys are corresponding. And then I also have this middle point to the right angle, or I could go right angle to the middle point here. Either way, it's not a big deal, but middle point to the right angle. So these two are corresponding because they're doing the same thing. It's going from the middle to the right angle, middle to the right angle. Or if I read it the other way, right angle to the middle, right angle to the middle. Either way, as long as I just can describe it the same way. So again, you can use it their way where you're naming all the vertices and showing, which sides correspond to each other, but you can also use this kind of visual direction. It's just up to what makes a little bit more sense to you. I think I'm going to make this a little bit bigger. The pen's a little small. It's just writing teeny tiny to me. All right, so we're going to write a proportion using these so that we can compare. And we've done this. We were doing this in chapter 6, so this shouldn't be brand new to us. Hopefully we've gone through all those sections and we understand that we can compare corresponding sides to each other when we have similar triangles. And the reason is, whatever I increased 7 or 5 by to get to 7.5, so it's not a whole number necessarily, it's part of a number, but I increased 5 to get to 7.5. Whatever I increased it by, whatever I multiplied by, I would have had to do the same thing to x to get to 3, because they're corresponding sides. So that's why we can compare them. The sides should have been increased or decreased, and by increased I mean multiplied, by decreased I mean divided. So they should have been multiplied or divided by the same number, same ratio, or scale factor to get from one to the other. Okay? All right. So we're going to go ahead and we're going to look at the small triangle. You could also say the top triangle, however you want to do that, and large triangle. This is just going to help me remember I want the numbers for the small triangle on the top. I want the numbers for the large triangle on the bottom. Okay? So the small triangle, I'm going to say that 5 compares or corresponds to 7.5. So these two have two numbers in it, which we need at least one of our fractions to have both top and bottom, numerator and denominator, filled in, because that's going to be basically our scale. And then for the other fraction, for the other part of the proportion, we're going to look at the variable that we're searching for. So in the small triangle, we're looking for x, and that corresponds to 3. So now we have our proportion written, and we can go through and we can cross multiply. So I can go cross from top to bottom. 5 times 3 gives me 15, and that's going to equal, I guess I'll do this other guy in red, if I go across the other way, 7.5 times x, which is just 7.5x, like that. Because we just kind of squish them together, right? So now we have this piece. I have to get x by itself, so I need to take that 7.5 and divide on both sides. And I believe we're going to get 2 here. So we'll go ahead and put this in the calculator just to make sure I'm not losing my mind. Yay! 15 divided by 7.5 is 2. So x is 2. And that compares. That's the same ratio, 2 to 3, is the same ratio that 5 and 7.5 are. So they're kind of the same difference, or same multiplier there. I know that sounds funny, but all right. So we'll go ahead and do 2. 2 is not the multiplier. I don't want you to think that. 2 is actually the length of x. So if we wanted to know what the multiplier was, we we would have to reduce either 2/3, which actually is reduced. That would be the scale factor, 2/3, which we could reduce 5 and 7.5 the same way by taking 5 and 7.5 and taking the decimals out. So if I move, dang it, if I move this decimal over, I'd have 75. I have to move this over once because I moved that over once. So I'd have 50 over 75. Well, if you kind of think about these, they can both be divided by 25. This can be divided 2 times. This can be divided 3 times. So I can do that same thing with this. That's not the only way, of course, to do that. I could have also looked at, how many 0.5s are in 5, how many 0.5s are in 7.5. That would have gotten rid of the decimal and then reduced that. A couple different ways to reduce decimals when we have fractions. But really the scale is 2/3. So 3 is 2/3 of, 2 is 2/3 of 3. I was saying that backwards. Because 2/3 is smaller, right? All right, let's go ahead and check that. Yay! Okay. We will. No. All right. So now, indirect measurement is a way of measuring things that would be very difficult to measure kind of actually with a measuring tool. But we can find the measurement of things using other things around them, especially if we have similar triangles. So let's read this problem. A pole that is 3 meters tall casts a shadow that is 1.34 meters long. At the same time, a nearby tower casts a shadow that is 38.25 meters long. And how tall is the tower? Round your answer to the nearest meter. All right, let's draw a picture because it's way easier to picture this, actually looking at it. So we have kind of a pole, and I'll put like a little circle on top, like a weird little flagpole, I guess. I don't know. And this guy is 3 meters tall. And it casts a shadow. So here's my very awesome shadow for my flagpole or whatever pole this is. And it's 1.34 meters. Oh, should it have been that long? Probably not. Let's shorten that up just a little bit just to, what's going on? I'm going the wrong way. So I'll make it very short like this. 1.34 meters. I should have looked at that before I started drawing the shadow. I read it and it didn't stick in my brain when I started drawing. So here's the pole, here's its shadow, right? And then it says nearby there's a tower, and the tower casts a shadow that is, and I'm going to make this a little bit bigger. It's a tower seems, that's going to be a little bit wider, right? And we're just going to call that good enough. It's 38.25 meters. I know that's not comparable. We don't have to draw them to scale. We're just kind of drawing a picture to help us match it. But here's my tower. So there's my tower. Kind of a weird tower, I know, but there it is. I'm not really sure what it's supposed to look like. It's just a tall building. We don't know how tall this tower is. It says, how tall is the tower? So I'm just going to say T for tall. I don't know. And it wants us to round our answer to the nearest meter. So we're going to round it off when we get it. Well, how do we know that these are comparable triangles? I don't see a triangle yet. So when we're looking at the triangle, and I'm doing this in yellow on purpose, we have the sun shining down here like this. So the sun is shining down, and that's what's casting the shadow. This is blocking the sunlight, so it's causing a shadow here. So same thing, if I were to scroll down here, and let's see, I'm going to try to do this nicely. Nope. I'll do it from here, like this. So, and I didn't draw these perfect. These two should be parallel lines. They look not too horrible, honestly, as far as parallel line goes. I don't think they're perfect. They definitely would clash into each other at some point here, but close enough. So, and again, the reason I'm using yellow is it's kind of like the rays of sun coming down, because we have the sun, very far away, casting this light down, and whatever's in the way of the light is creating the shadow. So this angle that's created is going to be the same by the sun, because it's in the same position in the sky from the flagpole to the tower. Okay, and they say nearby because that does matter, based on how you're on Earth and stuff, where the angle of the sun would be. So as long as we're nearby, it's the angle's not going to change. The other angle that would also be the same would be this guy that's down here, the angle created at the ground of the rays of the sun. That would also be the same, for the same reason as the top one is the same. The sun is in the same position in the sky, shining down at the same angle. So this angle of elevation here would be the same as the angle of, this is called the angle of depression, which I know students always get a little giggle out of that one. The pole and the tower we're going to assume are at a right angle to the ground. So they're perpendicular to the ground. So we can actually show that all three angles of the little triangle created by the flagpole are congruent to all three angles of the large triangle created by the tower. That doesn't mean they're congruent, just means that they're similar. All we need are two of the angles. We just need angle, angle. So that's why I went through and just showed you why this works. It's based on the sunlight coming down at the same angle. Okay? So we're going to do the same exact thing we did on the last one. This one I think is a little bit easier to compare because we have the height of the object or the shadow of the object. Okay? So we have the pole and we have the tower like this. And then I can say the, let's see, we'll go with height on this side. Why not? Height. And we'll go with shadow. So I can actually give myself a little map of how to fill this in. So the height of the pole goes on top here. That's 3 meters. The height of the tower, that goes on the bottom. Well, I don't know that. That's t. The shadow of the pole, that goes on the top on this side. So, and then the shadow of the tower, that goes on the bottom. 3, 8, 25, like that. So it gives me like this little map. We just want to make sure it's comparable. So the heights would be comparable to each other. The shadows would be comparable to each other. So this one's, kind of like directional on that other one, but we're comparing the actual kind of object, I guess, if we think of the shadow as an object. All right, so we're going to go through and we're going to do our cross multiplication here. So we're going to have 3 times 38.25, and I'm not going to do that one in my head because I don't want to try to mess that one up, times 3, so 114.75. I don't know why there's 2 ones there. Go away. 14.75, there we go. Equals, for whatever reason, I'm very worried about this color coding. All right, and then we have t times 1.34. So this is the idea, cross multiplication. And again, we practiced that quite a bit in chapter 6. So we're just continuing this idea. When we have a fraction equaling a fraction, we can use cross multiplication to get rid of the fractions so that we can solve the equation. So we have 1.34 t, because we just smush them together and it's proper to have the coefficient first instead of t 1.34. Really means the same thing. It's just it's proper to have it in front. That's what Alex will be expecting if it asks you to type it in this way. But it wants us to go to the next step. It wants us to actually solve for t. So I need to divide both sides by 1.34. I don't know why I said 3.14. I'm just going with pi on that one for some reason. Divided by, is it working? Divided by, there we go, 1.34. And we get 85.63, and that would be meters equals t, because anything divided by itself cancels out. So 1.34 divided by 1.34, even though they're decimals and, a little bit more complicated looking, it's still a number divided by itself, so it cancels out. All right, so it did say to the nearest meter. So 85 is the meters, and so we want to look at this one. I'm going to drop these guys off for a minute. I do need to look at this one before I completely delete it. This is going to help me know if I'm rounding. So 6 is 5 or bigger, so that means that I'm going to round this meter up to the next one. If it was 4 or smaller, the decimal simply just drops off. That's what rounding down means. Rounding down doesn't mean we actually change the number. It just means we round the decimals off. Rounding up means I'm going up to the next whole number. All right. Perfect. Okay, so now we're going to take a look at finding angles of similar triangles. I'm just going to go ahead and do a new one here because I don't feel like erasing all that stuff. Okay, so two triangles below are similar. So remember, even in a similar triangle, congruent, the angles are congruent. And I think, do I have a triangle here? What I could do is like this, because I can actually show you what I mean by this. So here I have this triangle, and I'm gonna try to lasso it real quick. Let's see if I can get this guy cut out here. Boom, like that, and I'm gonna copy paste. All right, so I made another triangle. So right now they are congruent. They're the exact size and shape. But what I can do with this program is I can enlarge it like this. But what I want to show you, the reason I'm doing this is I'm dilating this triangle. I haven't changed the shape though. I'm just making it bigger. Overall, all the sides are growing at the same rate. And if I take this and I try to line it back up, boom. Do you notice how those are the same down here? These angles, and I know that little thing is in my way. If I close it, then I can't edit this anymore. So I don't want to close it. But do you notice how those are the same? Now if I scooch this over, boom, look at that. This guy is now the same. And I can do the same thing for the top. Boom. Isn't that crazy? So I can also make this guy smaller, and it'll do the same thing. I can scooch this over and match. Match. And, oop, my stuff gets in my way. Match. So if you see that, I always thought that was kind of cool. That's definitely kind of different as far as that idea goes, because it doesn't seem like that would be true, but it is true. The angles don't change as you make an object bigger or smaller, as long as you're making all the sides bigger or smaller by the same factor. So you can't change the shape. It has to be the same shape, but you're just dilating it, meaning enlarging it or reducing it, just like you saw me do with that triangle. So if I'm looking at this one, it's the same idea. What I want to do is match up the corresponding angles. So G is 55. They have that filled in for me. E is 100 degrees. Again, they have that filled in for me. I need to know what F is because I'm going to have to fill in all three of the other angles for the other triangle. So I want to make sure that I know which ones match. And I'm pretty sure I'm going to do this on here because it's kind of cool to see this too. Let me grab it when it saves over here. There we go. Okay. So we have these two guys here. So I'm going to try to do my lasso tool again and see if I can copy paste. Oh, it's going to cover stuff up though. I don't like that. But it does let me rotate a little bit here. I wonder, you know what? Hold on. If I do that a little bit neater. I still didn't do that very nicely. It's a little bit funkier to do. Paste, okay. It's a little bit nicer there. All right, I didn't grab the letters because those would have gotten in my way, so we need to make sure that we can track 55 goes with G here, 100 goes with E. So the reason I'm doing this is so that I can kind of turn this so that we can see that this one does in fact come over here and fit right there inside. So if I get the right angle there, boom, look at those, that K matches right up with that E. And now I can kind of shrink it down too so that you can see that they, oop, why isn't it shrinking down? Why is it arguing with me so much? There we go. Nope. Doesn't want to shrink down so much. There we go. Now it's shrinking. I don't know why I was arguing. Okay. Guess it depends on which direction I do that. I still need a little bit more shrinking. There we go. So that's pretty darn close right there. Woo! Got it almost right on track there. So just by moving that over, I can see K is 100 and L is 55. Now I know you don't have the ability to do that, on your screen necessarily, but you can download this app actually. It's free. It's called Sketchpad. It's got a little pencil for its icon. Super cool. It just takes a little bit of getting used to with some of those tools. As you can see, I was fighting with it myself a little bit, and I've had this app for years. But it's a very cool drawing tool. Super helpful if you can kind of manipulate the pieces like this. You could also print this page out and, cut the triangles out, play with them. That's another, very plausible option if you have a printer at home. Or if you're at center, you could always ask us to print it for you. I'm not sure we could print it from your screen unless we had a picture, because we usually can't print to the printers from the students' computers. Weird little tidbit there. All right. So let's go ahead and fill in. We need to figure out how are we going to fill in that last angle, because we don't have these two guys here, right? So we need to remember, this is going back to, I believe, chapter 6, the triangle angle sum theorem. And all that says is that the three angles of a triangle, no matter what triangle it is, it does not matter. Even those, the dorky little triangle I drew here, as long as it was straight lines, I didn't do that very nicely, all the angles add up to 180 degrees. That's what the triangle angle sum theorem says. So if I have 55 plus 100 plus, we'll call that x, these guys have to add up to 180 degrees. That's the triangle angle sum theorem. So I'm just going to go ahead and add together these guys. I have 155 plus x equals 180. So now I'm going to subtract the 155 because I want to know if I can have up to 180 degrees total for all three angles, and I'm already using 155, what's left over? So when I subtract that, 155 minus 155 cancels, and I get, let's see, we're going to borrow, we get 5, we get 2, so we get 25. So this guy's 25. So F is 25, J is also 25. So I can go through now and fill these guys in, 25, 100, and 55. Okay, so we have one more of these. All right, so with this one, I'm going to go ahead and give myself a new screen here. We're going to use the same idea as we did on the last one there with the triangle angle sum theorem, because what we're going to do is we're going to compare these two triangles and all the sides, and then make a decision on whether or not it's congruent, or not congruent, sorry, similar, based on our findings. So we need to go through and fill in all the angles, and we need to fill in all the sides and compare the ratio of the sides, because that will give us an idea of whether or not they're similar. So first, let's fill in the angles here like they're asking. So we have ABC, we have angle A is 41, and then we can also see in DEF, D is also 41. So these match, that's good. B is 56, and E is 56. So remember, triangle angle sum theorem says that they must add up to 180 degrees, all three angles. So they're asking, what is angle C and what is angle F? Well, if I'm using the same angles here, when I subtract from 180, whatever this adds up to, it's going to be the same for both. Whatever's left over is the same, because I'm doing 41 and 56. I'm going to subtract that from 180. For angle DEF, it'd be 41 and 56. It's the same equation. So instead of writing it out, 41 plus 56 plus x, or angle C, equals 180, what I'm going to do is just combine these. So 41 plus 56 is 7, so 97, if I add these two guys together. So I'm using 97 degrees of the 180 that I have available to me. So I'm going to subtract, so I have to borrow again here. So this would be 63. So 63 degrees for angle C, and angle F. These will be congruent as long as these guys are congruent when you start with. If you have different amounts here, then they might not be congruent. Doesn't actually mean that you won't have similar angles if they kind of gave you different ones instead of giving you the corresponding angles congruent. So they, by chance, gave us the correspondings on this one. It's the intro to this idea, so I think they'll do that with you as well when you have your practice problem. All right, use the ruler to find all side lengths for each triangle. Assume all lengths are whole numbers. So we have this ruler feature, and we actually have to go through and measure these. If you did this in class with me, I know I had you cut out a ruler or use one of the rulers I had available in class to do this. So with this guy, that looks like 6 to me. I lined it up to B, and I have 6. So AB, I'm going to say is 6. And then I have to click it again, and I go A. C, that looks like 5. So CA is 5. And this looks like 4 maybe. So if I don't click, I can actually use it more than once. 4. All right, now we have, I have to click, darn it. So it looks like 8 for EF. And FD looks like 10 and 12. So FD was 10 and this guy looks like 12. DE is 12. Yes, okay. I just want to make sure I typed those in right. All right, so here are all the side measurements, going through and using that ruler. Now find the following ratios. Write your answers in simplest form. So they want us to compare AB to DE. Now if I look at this, AB are the first 2 letters and DE are the first 2 letters. This is corresponding order. So that's actually how they're written, is in order of corresponding angle. Well, I know A corresponds to D. B corresponds to E. So AB and DE are corresponding to each other, those side lengths. That's a quick little way to read that. So if I go like this, they want it in simplest form though, so they're not going to want 6 over 12. They're going to want me to divide that down. 6 can divide by itself once, and 12 can divide by 6 twice. Now BC and EF, so 4 over 8, that's the same idea. I can divide 4 by itself once. I can divide 8 by 4 twice. And then same thing here, 5 and 10, that's also going to give me 1/2 because I can divide both by 5. I don't want to change these ones. I want to change it in the ratio here. So we want to see this same ratio. This means that from one triangle to the other, we're changing by the same amount. So from the smaller triangle to the larger triangle, it's half the size. So this small triangle, I'm going to turn that off. The small triangle is half the size of the large triangle. Or the large triangle is twice the size of the small triangle. We can kind of look at that either way. But with the half, it just means that the large triangle is half the size. So all of these side lengths, if I look at AB, it's going to be half as big as DE, and that's true. 6 is half of 12. So it's just the way that we compare that. So now we're going to answer, for each one of these little groups, if you notice they're kind of grouped, we're going to click one of the answers. So 3 pairs of statements are shown below. For each pair, select a true statement. So the angles ABC have the same measures as the angles DEF. Well, that was true. We found the same ones. If we didn't find the same ones, we would click here. They do not have the same measure angles. And if we can't match up all 3 of one triangle to all 3 of the other triangle, they're not going to be similar. So we need to be able to match them up at the end here. Whether or not they give us the corresponding to begin with, at the end we should be able to match 41 to 41, 56 to 56, 63 to 63. All right, the ratios of the corresponding side lengths are all equal to each other. Well, that was true. They're all 1/2. If they weren't equal to each other, then again, we would not have a similar triangle because it would mean that one side was increased or decreased by a different number. Remember, just like you saw me dilating that triangle earlier, I was enlarging all sides the same. I was just enlarging the entire figure or shrinking it by the same amount. So the triangles are similar because the angles are congruent and the sides are corresponding sides have the same ratio. If I answered no to either one of these, they do not have, I would say they are not similar. Alrighty. Uh-oh, your answer in part A is incorrect. Did I subtract wrong? 5, 6, 7, 8, 9. Oh, ha ha ha. This should be 83. I know how to subtract. 8. They're still congruent. I just subtracted wrong. Silly person that I am. All right, let's try that again. Ta-da! All right, so that was section 5. I will see you in section 6.